morning, class. Welcome to today's session. Today we are going to continue with our programming languages. This was started during our last online session, whereby we discussed that we realized that we have several instructions which can be used to program the Intel 885. And these instructions can be grouped into instructions which can manipulate data. We have instructions which can transfer data. We have instructions which can perform control functions to the CPU. Now, this is a continuation of that lesson. Remember, we were remaining with the two learning outcomes. So this one is a continuation of that lesson. So welcome and join me. Remember also this lesson is very important for you because for you to understand how to write instructions, it's very important for you to know how those instructions fetch data. And we are going to discuss that one under today's session, which is actually addressing mode. So at the end of this session, you should be able to explain various addressing modes and then also write application programs. This learning outcome actually is going to be your assignment for the end of this topic. Remember, this is the end of this session will mark the end of this topic, that is introduction to assembly language, programming of Intel 885. And now maybe you are asking yourself, what are these addressing modes? Just understand this is also grouping of instructions into different modes of how they access data. We have instructions which are they are accessing data which are stored in the registers. We can have an instruction which is addressing data which is stored in the memory. We can have an instruction which is addressing data which is inside your mind, your thought. So we are going to see these different instructions. So how these instructions work on their operand is called what? Addressing mode. So anytime when we write a program for the microprocessor, each instruction needs some data. You remember this data is an operand, and you remember I told you that microprocessor, the instruction are made up of two parts. The first part is we normally call this part the opcode, and then the second part is the operand. Now this operand, now whenever we write an instruction for the microprocessor, every instruction, or not, of course we do understand not all instructions must contain an operand, but whenever we have an operand, there is a way this microprocessor is going to work on this operand. Now addressing mode here is the way the processor finds this data. So remember, this data, which is the operand, can be inside the register. This operand can be inside the memory, or this operand can be inside our mind, your thought. For example, here, this is a number which is 144, which is a decimal number. If I want to insert this data directly to my instruction, then I have to use this type of instruction where I'm going to load this number to the accumulator. Maybe you are now confused. Why are we having 90H yet 144 is the one which is inside our mind? Remember, the computer is not going to work with the decimal number. They are more efficient working on the hexadecimal number or binary number. So now you have to convert the number from the decimal number to hexadecimal for you to insert inside the instruction. So these are just few examples of how the microprocessor, when executing an instruction, is going to work or not on the operand. And I've said the operand can either be inside the memory, can either be inside the instruction, the register, or inside your mind. So we are going to look at this different addressing mode one by one with some examples. So number one of this addressing mode is the register addressing. So in this register addressing, remember that the data which is the operand, the data which we are working on are found inside what? The registers. So this instruction, most of the time you will get it, they are either moving data between the register and the CPU. And when I'm talking about the CPU here, I'm talking about the arithmetic logic unit. Remember, I've just put them inside what? The block. But inside this CPU, we have other blocks like a control unit. Another one is the arithmetic logic unit, among other components which form the central processing unit. So this register addressing, the data which we are working on, that is the operand, is either found inside what? The register, and we are either moving it between the register and the arithmetic unit or within the registers themselves. So we have some examples. For example, we have move to accumulator, what is found inside register what? B. So this instruction is going to copy data from the register B to accumulator. So it means that after this instruction has been executed, the data which is going to be found inside the accumulator is the one which was found inside what? Register B. Another example of instruction is add C or subtract B. So when I'm adding C, I'm taking what is inside the accumulator plus what is inside register C, and then the results is going to be stored back to the accumulator. So for example, add the content of register C to accumulator, and then subtract register D from the accumulator. So all these instructions which you see, they are addressing the register, we normally call them what? Register addressing. So another type of addressing mode is whereby you are addressing the register, but actually when you go inside the register, you will not find the data, but you will find the address to the memory location which contains that data. That one normally happens. So instead of you going to the memory and fetch data, you go to the register, you find the address of the memory location. When you follow that address of that memory location, you will find what? The data. We refer this one to indirect addressing. So you are not actually addressing the register, but a memory. So you are addressing the memory indirectly. Now, for example, I have an example here. Let's say I have a memory location, and this memory location is 20H and 21H. So in 20H I have this data, and then in 21H I have this data. So what I'm going to do, I'm going to load this register the address of this memory location, that is 20H and 21H, to register pair. Remember, this number is very big. Our register can only hold up to an 8-bit data. So if I have more than 8-bit data, let's say 16-bit data, I have to pair two registers for them to hold that data. And this is normally how we pair this register. We can either pair it HL to be together, BC to be together, DE to be together. So these are the only pairs which we have. So it means that you cannot pair A and B, for example, and you cannot pair H and D. So you can only pair HL, BC, or DE. And if you look at this alphabetical number, you'll see they are following each other. H being the upper one, L being the lower, B being the upper, C being the lower, D the same thing, and E. So now let us continue with this example. So I've told you that you cannot hold more than 16-bit data inside one register. So if you look at this 20H alone, it's an 8-bit data. 21H is another 8-bit data. So I'll need how many registers? I will need 2 registers to hold this data. Now remember, this is not a data actually. The data is found inside these what addresses. This is an address, yeah. So but it's going to appear like a data in what? Inside our register. So I'll take 20 to be held by register H, and then 21 to be held by what? Register L. And now when I'm writing the instruction, the instruction is going to go to the register pair, which is HL, and inside this register pair I'm going to find what? My address of the memory location. And when I follow that address, I'm going to fetch data from that memory location. So it's going to act like a pointer. Let's say if you want to know the direction of going to a certain place, you have to go to someone first, then that person will show you the direction. So that person is going to be like what? A pointer. So and that's why you see from this explanation, a register pair can be either HL, BC, or DE, acts like a pointer to memory. Instead of giving data directly, the instruction looks at the address stored in that register pair. We have examples here. Move to accumulator M. So M here being the address of the memory location, which is being held by what? Register pair HL. You can also move from the accumulator to go to the what? Register to the address which is held by the register pair HL. So copy content, copy accumulator content into memory address in HL. You can even stack V. So this store accumulator in memory location pointed by BC pair. Those are examples of what? Indirect addressing. And I repeat again, indirect addressing is whereby instead of storing the data itself to the register, you store the memory location to the register. And when the instruction is going to be executed, it's going to go inside the register, find the memory address, go to the memory address, fetch data, and work on that data inside what? The accumulator. So far, the first two examples which we've looked at, we've seen that the first one, when the operand is inside the register, then we do what is called direct addressing. The second scenario is whereby the data which is inside the register is not actually the data itself, but an address to a memory location. And we say that one is what? Is an indirect addressing. You see, in the first two examples, it means that data is inside either the memory or inside what? The register. Sometimes you learn to insert the data straight from your mind to the instruction. So it means that this data is not stored anywhere. It is just inside your mind, and you want to put inside the instruction directly. So the data itself is written inside the instruction. Very simple, but less flexible. Yeah, it is very simple, but it's less flexible because the data which you are going to work on most of the time should be what? Should be less than it should be at most 8-bit data. Of course, if it's an 16-bit data, it's going to be, you are going to require a register pair to hold that data, and that's where we say it's less flexible. So an example, for example, here I have move immediately, MVI. So move immediately 25H, which is an hexadecimal, so it's 25 hexadecimal number to register B. So this one is load number 25H directly into register B. Remember, this data is not found anywhere. You've just inserted it straight from your mind. And then we have another one here. So MVI, so move immediately to the accumulator. What are you moving immediately to the accumulator? 99H. So let's say you have 99 hexadecimal number in your mind and you want to insert it inside the instruction. So there's no need for you to store this data anywhere. You can just insert it inside what? The instruction. And this is a good example. So add immediately. So we can also add the content of the accumulator with what we have inside our mind, which is 05H. Remember, 05H is equivalent to 5 in decimal number. So add 05H directly to accumulator. So these are immediate addressing. They are very, very simple. You are working on the data which is inside what? Your mind. And that data you insert directly to the instruction. Most of the time you will see this instruction ending with what? Letter I. Anytime you see this type of instruction which ends with the letter I, we say that is what? Is an immediate addressing. And whatever is going to follow as an operand is a data which is just found inside what? Your mind. Now I have an example here. For example, I'm moving immediately to a register destination RD. RD can either be A, B, C, D, E, H or L. And because I'm moving the D8, D8 is an 8-bit data. So you are loading an 8-bit data to a destination register. And this destination register RD can either be what? Either of these. Remember, this is an 8-bit data, so you can store it in an individual register without pairing them up. So this is the illustration that the 8-bit data is going to be moved or to be stored into the register, destination register. So an example here, you are moving immediately to register D, which is you are moving 9H to register D. So at the end of this instruction, D is going to contain a number which is what? 09H. So before execution, let us assume inside D we had a data which is C2. So after moving this data to D after execution, the register D is going to have what? A new operand. And this operand is what? 09H, which was inside our instruction. So another type of addressing mode is whereby I'm working on a data and that data is inside a memory location. So this time around, this memory location is not held by the register. So I'm working directly with what? With the memory. And that's what is called what? Direct addressing. The instruction gives the exact memory address of the data. For example, here I have an instruction whereby we are loading to the accumulator 2050H. So this is an instruction. It's a type of instruction. But this instruction, we are going inside memory location 2050H. What we are going to find inside this memory location. So this is our memory. These are locations. One of the location we have their address is this one, and the address of that location is 2050H. So by executing this instruction, we are going to go through inside this memory location, which is this, and we are going to find this data. So this is the data which is going to be loaded to the accumulator. And remember, accumulator is one of our register, so it's going to be inside our register bank. So that is a direct addressing, because we are directly addressing what? The memory location without passing through what? The register. Remember the other time, instead of going directly to this memory location, we were going first of all to the register. We load the memory location from the register pair, and then we go to the memory location and find the data. That one is indirect addressing. But direct addressing, the instruction gives the exact memory address of the data. We have other examples. So this one is the first example which is being illustrated here. So load data from memory location 2050H into accumulator. So maybe you are wondering, why are we having memory location the same way maybe we've seen other data? So remember, all memory locations are given in what? Hexadecimal number. All memory locations are given in hexadecimal number. All data we are working on can either be in binary form or hexadecimal number. Remember that again. So we have another example. So here we are storing what is inside the accumulator to go to the memory location, that 3000H. So store accumulator content at memory location 3000H. And then this one we have LHLD to 2500H here. We load HL register pair directly from memory 2500H and 2501H. So remember, if I want to load the address of the memory location to the register pair so that later I will do indirect addressing, then this is an instruction which I should execute. So LH, so I'm loading to register pair LH. And what are you loading to this register pair? You are loading the memory address, the memory address, which is this one, and the adjacent memory location, which is going to be 2501H. So that those two memory locations are going to be held by the register pair HL. So these are examples of direct addressing instructions. So another addressing mode is the absolute addressing. Absolute addressing is similar to direct addressing, but often used in large processors. Processor where the full address, that's the absolute address, is specified. So most of the time, this one is the word like a direct addressing. So it means that we are addressing the memory location. But now these instructions, they help the microprocessor to execute the program very fast. For example, if this is the next instruction which I was supposed to work on, remember, any data you are supposed to work on it next time, or my next round, the address of that instruction is held by a special register which is called program counter, PC. So the PC is a special register which is going to always hold the address of the next instruction. So let's say the next instruction was found in this address memory location. So we have this memory location. So instead of me executing this instruction, I can jump to another memory location and execute another instruction. So instead of following the instruction in ascending order, I can jump between the instruction. Sometimes that happens. So what I'm trying to say, sometimes when we are running our program, we are not always executing the instruction in ascending order. No. Sometimes you'll find advanced microprocessor, we are executing several instructions in this memory location, and then we jump to another memory location and execute another instruction instead of following in this manner. When that happens, we are doing what is called absolute addressing. For example, an example here, jump to memory location 5000H. So jump to instruction at absolute address 5000H. So instead of going to the next instruction which was found in this memory location, we've jumped to another memory location whereby we are going to find the target instruction. We have good scenario. We have a lot of application when it comes to this one. For example, when we are executing an interrupt, remember, an interrupt is something which is going to hold the microprocessor from continuing with the normal task. We are going to force the microprocessor to hold what it's doing currently and then execute our interrupt. And for example, a good scenario in the industry, let's say we have a microprocessor which is running the motor. So we are executing instruction as we run the motor, but we find out that let's say a person is exposed to the moving parts of that motor. So the sensor is going to pick that one. So instead of continuing with the process of running the motor, we are going to jump to the instruction which is going to force the motor to stop. And when we need to execute that instruction, we have to jump to that memory location. And this is when absolute addressing comes in. So other type of addressing mode we have relative addressing address is not given directly. Instead, a distance, that is an offset, is given from the current program counter. Are mostly used in branch instruction. So like you also see this one and also the last addressing type, that is absolute addressing. They are almost similar, but this one again we are not giving what the address of the operand, but instead we are going to give what an offset from what we are working on currently. For example, here we have gen z label, so jump to label if zero flag, if flag is equals to what, 0. Then we have jc target, jump to target if carry is equals to what, 1. Then jump next, you jump if 0, if flag is equals to what, 1. So you jump 0 if flag is equals to 1. These are type of instruction whereby you are going to branch to another instruction after something has happened. So we have to depend on a certain parameter for us to what, to jump, and this one is called relative addressing. So we are addressing an instruction which is relative to what we are currently working on. And then we have indexed addressing. So this is effective address is equals to base address. So so we have an address inside the register plus an offset given in the instruction. It is useful for accessing arrays of tables, not directly supported in 885 but common in advanced processors. So you will not find this instruction used in what, 885. You will find them used in 886. So that is it. So then we go to the last one, the last two instructions. So implied addressing is another type of addressing mode. In this mode, the operand is not mentioned because it is understood that is implied by the instruction. So most of the time you'll find most of the control address instructions being found here. For example, we have CMA, complement accumulator, RLC, rotate accumulator left, DAA, decimal adjust accumulator. And then we have another one which is stack addressing. So in stack addressing, data is stored and accessed from the stack, that is last in, first out. Remember, stack is a section inside RAM. It's a special memory location which is set aside inside the RAM. And the work of this memory, which we normally call stack, is to hold the instruction which we are currently working on and which we finished working on the last time. So what I'm trying to say is a stack is inside a RAM. So it's a special memory inside what, RAM. The work of this memory is to hold data which we are currently working on, or the data which we finished working on in the last round. And that's why, and how do we store data in this memory? So the last in is going to be the first out. So because the last data which is going to come in is going to be on the top, so that when we want to retrieve the data, that one is going to be the first one to be retrieved. And that's why you say last in, first out. So instruction always work with the top of the stack. So anything we are going to work on is supposed to be on the top of the stack table. So we have an examples here. Push B. So push contents of register pair B and to stack. So when you want to store data, so that you see if something is going to happen to our microprocessor, we have to retrieve the last data which we were working on. And this instruction, if you are working on the data which is held by register pair B, C, if we push those content to the stack memory, we can be able to retrieve it and know this where we stopped during our last instruction. This one normally happens, for example, you will see that you are playing a music, you shut down your phone. When you open your phone, you are able to pick exactly where you left playing that song. How is that possible? We push the last instruction, which is the operand of that song, to the stack memory. So when you want to resume playing, we'll go to the stack memory, retrieve the top data, that is the data which is stored in the stack memory, and we'll be able to resume playing music from where you left. So if we have another one which is pop B, so pop top up stack back into register pair B. So you can retrieve assume that when you wanted to shut down the processor, you push the content of register B to the stack memory. If you want to retrieve that data, then you have used this instruction. So that one is going to pop the top part of the stack back to the register pair. Then we have call 2500H. So push program counter to stack. So jump to subroutine at 2500H. And then we have RET, so pop return address from stack and continue execution. So those are the different addressing modes which we have. The main one are register addressing, direct addressing, indirect addressing, and also immediate addressing. Those are the main, but of course we have others like implied addressing, absolute addressing, stack addressing, and the list continues. Of course we have instructions which are very advanced. We cannot use them in the 885, but it's very important for you to know their addressing mode. So that's what I wanted us to discuss. So let us go through the summary so that we understand what we've covered so far. So we've discussed about addressing modes, and we've seen that when we are working on the operand, that is the data of the instruction, that data can be found as either inside the register, can be found either inside the memory, or can be just inside our mind. And we need to know these addressing modes for us to write our instruction effectively. So whenever I'm having an instruction which is working on the data which is directly found inside the memory, then that one is going to be direct addressing. If I have an instruction which is going to work on the data which is inside the register, then that one is called what? Register addressing, and the list continues. So that's what I wanted us to discuss today. So those are what I wanted us to discuss today. This marks the end of the topic, Introduction to Assembly Programming Language of Intel 8085. We started by looking at different types of instructions. We saw that we have instructions which can manipulate data. We have instructions which can move data. We have instructions which can control the microprocessor, among other instructions. Today we've covered the addressing mode of those instructions, and the addressing mode is ways of telling the CPU where data is. So that data can either be inside the register, the way we've said, can either be inside the memory, can either be inside what? Yeah, inside your mind. And it's good to tell the CPU where that data, where you are fetching the operand. I think we are going to stop there today, guys. Remember, I'm going to send you some questions, and these questions are going to be about application of what? Microprocessor. So make sure you go through the video, write notes in summary. Let us meet on Thursday during our normal physical class. I'm going to stop there. Enjoy your day. Thank you so much.